Once again, got my name tag, and half of the people here present have called me out, justifiably so. So welcome to the first session of Artificial Intelligence Everywhere, a huge topic that we're so appreciative Gary Morris has decided to take up for us. Gary is a HASC member. He has a BA in economics from Michigan State, an MSc in artificial intelligence, and a PhD in machine learning, both from University of Pennsylvania. He served as chief of the IRS AI laboratory and is an adjunct professor of computer science at Northern Virginia Community College. So without further ado, Gary, I'll turn it over to you.
Thank you, Kim. And I have one question for Susan. With our new setup, when we get to question and answer time, do I need to repeat questions or can the folks at home hear them?
No, you do not need to repeat them, but whomever is going to ask a question, make sure you have a microphone. I have one, Kim has one, and if you, Gary, have somebody ask a question and they're not mic'd, go ahead and repeat it. Okay.
Okay.
Thanks.
Just raise your hand. I'll come and find you. We can do two at a time.
Which is a great segue to saying, I think all questions are better when fresh. And if you ask a question that I'm going to deal with later or that is better suited for next week, I'll be not shy about telling you that. But if something is not clear to you, please raise your hand or put something in chat or whatever so that we can clear it up right away. Well, this morning is the first of two parts talking about artificial intelligence. And today we're going to talk about how things have changed in the 6 years since the last time I lectured about artificial intelligence everywhere. And the short answer is everything has changed. I'm going to define the categories of AI and try for each one to give you a definition of what that particular specialty is. Talk about some of the basic methods or algorithms that are used in that part of AI and where we see it in everyday life. And occasionally, we'll tell some stories about the background of these things or how we got there. Next week is when we'll get into all the controversial stuff. I will try to wear body armor. Next week, we'll talk about the economic issues, particularly facing robotics. And we'll talk about the social issues, particularly concerning AI. And we'll even talk about some of the legal issues that are now coming up concerning artificial intelligence. I think next week will be interesting, to say the least. Okay, well, in the last 6 years, times have indeed changed. Now, in 2011, just 11 years ago, Apple introduced this amazing breakthrough technology called Siri, and everyone said, "Oh, wow, it's magic." And now everybody carries that around in their pocket, no matter what kind of phone they have. And it's like, duh, everybody has that. Just 6 years ago, I gave a lecture called AI Everywhere. And I thought this was going to be big news to all the people in the audience. And by now it's like, duh, everybody knows that. The following year, I gave a lecture called Humans Need Not Apply, talking about the possible economic and labor issues when automation and AI worked its way through the US economy. And now, I mean, we don't even need a lecture like that. All you have to do is read the newspaper. It's something that everyone's talking about. So what is artificial intelligence? It's a good question. We've had over 50 years of AI research, and there still is not a commonly accepted definition of what AI really is. Now, my favorite definition is AI is building machines that can do things which, when done by humans, we call intelligent. But that's just kicking the can down the road, because during that same period of time, psychologists and psychiatrists have argued until they're blue in the face about what is intelligence. The only thing they've ever agreed on is we want to define it in such a way that we're the only ones that are. However, if you see dolphins swimming around carrying signs, you might wonder about that. One wag had said the best definition of AI is, if we know how to do it, it's not AI. It's just computer science. And one could argue that there's some truth to that. But one thing that we all agree on is that AI is machines operating alone without a human operator. Word processing is not AI because you are controlling mostly, unless you use Word, you're controlling mostly what the computer does. But speech recognition is AI. Even though you're talking to the computer, your voice is just data. The computer by itself is figuring out what that speech really means. A lot of people think that AI allows a machine to replace a thinking human being. And in some respects, that's true. You'll see later, an artificial intelligence program can interpret an MRI or a PET scan better than most humans. And I have a friend who's a radiologist who said, yeah, and it's about time because people make mistakes. The AI isn't perfect, but it's better than us. But on the other hand, that radiologist is not worried about losing his job because only another human being could
I
patient
thought I had, but I don't know how to turn that
what
on.
that MRI says. So yeah, AI is intruding on a lot of areas that are considered to be, very difficult specialties. But so far, they're not replacing human beings. They're simply enabling us to do a better job. You may have seen recently this headline that artificial intelligence may reduce false positives in breast cancer screening. If you read the article, you would find that a bunch of radiologists have developed, along with some computer science people, an AI program that can look at the ultrasound of a woman's chest and can actually detect breast cancers more accurately than a panel of human experts. Now, the human experts are pretty good. They get about 92% accuracy, and the AI only increases that to about 96. But if you look at it the other way around, 8% of all the human decisions are wrong. And every mistake either means that someone has to undergo an invasive procedure unnecessarily, or worse yet, that a small cancer was missed. The AI system cuts the errors in half. That's a big win for people. So again, AI is in a sense replacing a thinking human, but only the human doctor can sit down with the patient and talk about what the AI has come up with. Now, there are, in my opinion, 5 basic types of AI, and we're going to spend the rest of this morning talking about what they are, how they work, and what they do. The first area is natural language processing, which at one time was considered to be just one of the 5 categories, but it has proven to be so useful in society that it's now generally broken down into 3 subcomponents. There's speech recognition and generation. Then there's text understanding and text generation. And another one that we all appreciate now is automated translation. My favorite part of AI is machine learning. And you'll probably hear me talk more about that than the others simply because I know what I'm talking about sometimes. Computer vision is something that we are seeing more and more in society. Planning and decision making is something that you're probably not really thinking that you see in society, but I'm going to try to convince you that yes, you do. And finally, robotics. Everybody knows about robotics, partly because those clever people up in Boston keep producing robots that can do amazing things like backflips and climbing over stairs. Let's look at natural language processing, and I'll try to give you some definitions. Speech recognition is converting sounds, your voice, into text. Speech generation is converting text back into speech. Text understanding, at least at its basic level, involves converting a written sentence into something that is structured data. For instance, if we have the sentence, "The brown dog licked my face," a very basic text understanding program would divide that into a bunch of objects. The first object would have the word "the," would define it as a definite article, and would have a pointer that says, "This modifies dog." Another object would be brown, which is an adjective modifying dog. The dog object would identify it as a noun and also as the subject of a verb. And then the would be another modifier of dog, excuse me, licked would be a transitive verb, which means that it has to transition between one object and another. So it would identify what the two pointers are, my and face and so on. That's basic. And almost every text understanding program now can do that quite well. Advanced systems, quote, know the meaning of dog, brown, face, etc. Now, I put it in quotes because that's still very much a work in progress. And we're not even sure what it means to say that a computer knows what a word means. Text generation is something that we're seeing a lot more of. It's defined as simply creating a grammatically correct sentence that expresses a known relationship or action. Again, you have to use your imagination about what it means for the computer to know something. But given something that it's trying to express, text generation programs these days can generally create grammatically correct sentences, which puts it one step up on most teenagers. And we see this in automated translation, like Google Translate. We also see it in automated story writing. And even recently, we've seen that text generation programs can generate a whole paragraph just given a brief seed sentence. Now, in speech recognition, originally, the methods used were simply to try to take recordings of one person's voice and ask them to pronounce a whole series of words and kind of learn how that person speaks. 25 years ago, if you used Dragon, or I think Microsoft had a product, I forget what they called it, you know, you had to go through this extensive training process to try to get it to understand your voice. And frankly, sometimes it worked and sometimes it didn't. If you were from Maine or Georgia, you know, good luck. But currently, they have found that a much better approach is not to try to learn one person's speech. They train a deep learning system, a type of machine learning, on millions of voices of every kind. Spanish speakers and French speakers and you know, Georgians and Texans and you name it. And they've come up with universal models that work beautifully on almost any voice. Now, where do you see it in modern life? Just about everywhere. I mean, you've all seen Siri and Alexa and all those other things where you can command your home systems or tell your phone what to do just by using your voice. And those systems work extremely well. I'll bet every one of you has one of them in your pocket or your purse. Also, if you have a computer or a pad that for some reason you want to voice control, almost all modern equipment, you can turn that capability on. You have to then be careful what you say, but you can control modern computers simply using your voice. And for someone who maybe is dumb enough to almost cut his finger off in the workshop, it's really handy for a while. Phone menus are another example of speech recognition. If you call Walgreens, you'll find that you get a recognizer that answers the phone and says, you can tell me what you want to do. And that system works pretty well because there's a pretty limited vocabulary for drugstores, right? But on the other hand, if you call customer service someplace where you could be talking about anything, you've probably experienced some frustration because when the words you speak could be about almost any topic, that's still a little bit hard for speech recognition. Now, in text understanding, we aren't nearly as far along as we are with speech recognition because language is really messy and complex. And even when we write it down, it's hard to understand it. I mean, heck, sometimes you look at what people have written to you and you wonder, huh? A machine has a pretty tough time. Now, originally, the thought was that if we can just come up with rules that identify the part of speech for every word, like in that example I showed you about the brown dog licking my face, that would really solve most of the problem. That was wrong. Very limited success came with that. Much later, when machine learning became more powerful, they decided, we'll just train a machine learning program on millions of documents, and that will help us to predict common word groupings. It'll help us to predict the most likely part of speech in any one context. And frankly, that method worked a whole lot better, but it's still got a ways to go. The most advanced systems these days use a combination of machine learning and rules, and they're getting better and better. But we are still not to the point where you can talk in general terms to a machine and have it really get it. But this is useful enough that you're seeing it in a lot of places. When you do a Google search, the search terms that you put in that box are text, and Google is going to have to try to understand that text in a fairly sophisticated way, because you may put in some misspelled words. You may say the word football where somebody else would say soccer. And Google has to figure all that out. And they have systems that do it pretty well. Also, when you go to a website for a company, quite often something will pop up in the corner that says, would you like to do an online chat? Well, if you say yes, the first thing you're chatting with is not a person. You're chatting with a text understanding system. And again, if the vocabulary is somewhat limited, you may have some success there. I usually don't. So, you have to figure out how many ways can I say, let me talk to a human. A lot of you have grammar checkers on your computer. And a grammar checker, as any English teacher could tell you, can't simply look at a word or a couple of words and tell you whether that's grammatically correct. You really have to understand the whole sentence and what it's trying to do in order to determine whether you want TO, TWO, or TOO. Grammar checkers these days do an extremely good job of that, and it's because they are understanding the text as you write it. Now, text generation is, in effect, the reverse of that. And there have been some recent very dramatic improvements in that. Their methods, once again, use machine learning. They have applied neural nets to billions of text examples and have learned how to create natural sounding sentences and paragraphs. And if that sounds difficult, you're right. This has taken decades of research by a lot of dedicated people, but again, machine learning has kind of ridden to the rescue, and it's now fairly possible. Where do we see it in real life? Well, Google search responses. If you put in a search on something like, cranes in the city hours, it will not only understand that you're trying to find out what are the hours of operation for a restaurant called Cranes in the City, but it will scour the net to find that information, and then it will generate a summary. What would happen if you did a Google search on HASP Holland? Well, what you'll get is this over in the right side of your screen. Now, this is not the HASP website. This contains information taken from the HASP website and from any other place on the web it could find that talks about HASP. And then everything on this screen was generated by a text generation system. So, and it's all done on the fly. This is not pre-computed. It's done on the fly for every query that you make, and it always is done in less than 1 second. So let's say you were to Google how to add memory to a Mac. Here's what you're going to get. First of all, they'll brag, 238 million responses were scanned in less than a second. And then it's going to give you this set of instructions on how to upgrade the memory on your Mac. Now, this is not taken from any one website. This is a summary of lots of websites. And in fact, it's also wrong, because there's a lot of bad information out there. And the one thing Google can certainly not do is discern between good information and bad information. Do we have a problem?
Yeah, I've been monitoring at home. Your presentation is up, but it is not up in the classroom.
Oh.
We'll see what I can do without disrupting you too much.
Okay. So since you're not seeing this screen, maybe I should read more of it to you. One of the most dramatic things that's happened recently is something called GPT-3. And if you read the tech news, I'm sure you've read a lot about it. Still didn't come up.
It might in a minute.
Okay. GPT-3, it stands for Generative Pre-trained Transformer, which doesn't tell you much. This is a system that was created by OpenAI, which is an interesting organization by itself. It's a group of computer scientists who work basically as volunteers, or sometimes they're supported by philanthropists, but everything that they do is given free to the academic community. It's a nonprofit AI research lab. And they have done some rather stunning work. GPT-3 is just one example of that. What they've done is a language model. And that sounds like something fairly simple. It has billions of parameters. I can't even conceive of something that has billions of parameters in it that could make any sense. But in fact, these guys have developed a machine learning program that can generate a model that has billions of parameters. Boy, at this point, I really would like you to be able to see the screen because I'm going to show you some examples. So we pause at this point to say, well, do you have any questions so far? You want to wait just a minute for the microphone?
Hi, Tom Reddick. I was a speaker on a panel with Mustafa Suleiman from DeepMind at Arizona State, hosted a Future of the Human Race. I was talking about genetic editing. He was talking about integrating AI into the human beings and how that would change the human race. Is that anything we're going to talk about today, or am I jumping the shark here to go ahead to your later agenda?
Well, we can certainly talk about that next week when we talk about social issues and legal issues, but not today.
I'll definitely come next week then. Thank you.
Well, I'm glad we got that commercial out. Any, okay, we're giving up on the screens here. Oh, we're rebooting them. Okay.
I am able to see the screen.
Okay. Okay. Any other questions? Again, I'm trying to kill time because I want to show you an example of what GPT-3 can do. And I really would like you to see it. But we have a question over here. Kim?
Since you're filling time, it isn't that important. But first, I wanted to say, in spite of computer failure at the moment, you're doing a great job because we're all following along. Well, but what did I've heard a lecture by that group before, but I forgot what GPT stands for. I'm not a
GPT is Generative Pre-trained Transformer. Generative in the sense that it generates things, but it's pre-trained on these hundreds of millions of documents that it's already seen from all over the place. And a transformer, which means that it takes some kind of internal representation and transforms that into English, in our case. And I don't want to get too far behind, so I'm going to now bore you with my speech. GPT-3 is something that you can find on the web and you can play with it. I did. I input something, said, Bob was frightened by the loud sound. Fairly innocuous. And here is what GPT-3 instantly produced. Bob was frightened by the loud sound. His heart thumped wildly against his ribs. He tried to focus his eyes to see what it was that had made the noise. He could see nothing. There was only the eerie darkness. He could feel the floor moving beneath him. He could smell the air. It was full of smoke and the taste of ashes. He could see the walls of the cellar, and then he could feel something, a weight on his chest. Someone was lying on top of him. It was the old man. Edgar Allan Poe probably would have liked this. But that was the input that this system produced simply from the output from my input of Bob was frightened by the loud sound. I think that's pretty amazing. I was so impressed with that result. I thought, okay, I gave it too easy a job. We may be making progress here. Huh? Well, meanwhile, I'll continue reading to you. I thought, okay, that was too easy. So I gave it another input. This was like maybe 3, 4, it was before the Super Bowl. The Bengals were a long shot to go to the Super Bowl. That I thought would really challenge it. And here is what GPT-3 generated. The Bengals were long shots to go to the Super Bowl. They were lucky to make it to the AFC Championship game. And the final game of the season was going to be played in a dome in the middle of the coldest region of the country. The Bengals were also lucky to have a bye week, and that had to be taken into account when trying to predict the final outcome. The Browns, who had already played in one AFC Championship game, were not going to be an easy team to beat. They were a better team on both sides of the ball, but the Bengals were playing the same team that they had beaten in week 2. After a wild and crazy game, ... it stopped there. I'm still blown away by that. A machine created that story fragment with no human guidance other than my input of the Bengals were long shots to go to the Super Bowl. This generation engine is freely available to anybody for research or just fun, or to create commercial products. Because it was created by OpenAI, anyone can use it to further the technology. And already there are dozens of commercial products being offered on the market that use this engine for specific purposes to try to help businesses. As I said, yes.
I give you an option. I need about 2 minutes to reboot the system. That's really my only option right now. So
Okay.
you can try or put it into
Several times. Okay, I will step away from the camera.
I think the people at home will, well, for a moment, they won't be able to hear you if you could tell them that. Please.
Okay, I'm going to go silent for a minute while we try to reboot the entire system. And this is an exclusive question and answer period for the people here in the room who paid extra for this privilege. Okay, we have some questions over here. Wait for the microphone.
The GPT-3, do you think it's actually creating that feed, or is it compiling it from different things that it finds on the web?
Well, that's a very insightful question. Obviously, what it, quote, knows about Bengals and Super Bowl has to have been gathered from information that it found on the web. But to have taken all that and then put it into that very well formulated sentence that talks about the challenges, the sequence of the AFC Championship game before the Super Bowl, that is the result of a machine that has literally tens of billions .
The question I have is, lately, Alexa has been asking me to identify myself to it so that it could, I'm not sure what. What can I expect to gain if I identify my name to my voice and my wife does the same?
I'm speculating here that Alexa would like to be able to address you by name. However, she asked if you're happily married.
Gentleman right there.
Is my mic on? Okay. Question over here.
How does one access this?
Oh, if you just put into Google GPT-3, there we go. If you just put that search term into Google, it will give you as probably your top hit the website that OpenAI has created, where it'll say, you know, give me an input. It's fun. Okay, question back here.
This is more of an observation. A couple of years ago, my daughter had knee surgery, so I went to California to visit. And she likes talking to her phone. She was bored, so she's in the basement, laid up, asking her phone to tell her jokes, and it did. And so she's sitting there doing jokes back and forth with her telephone. And finally, she made some kind of smart aleck remark. I was sitting there, and her telephone came back and said, "That's not very nice, Kimberly."
Anybody
Okay.
else?
One more question, or now we can go back to the live. Okay, one more right here. Kim.
This is a very rudimentary question, but why is this important? Well, how is this useful?
Well, that's a very good question. What can you possibly do with this? Let me suggest that when you are reading the recaps of baseball games in the newspaper every day, next, if we ever have baseball again, it is very likely that you'll be reading recaps of the game that were written by this system or one of its offshoots, because the statistics that are generated from every baseball game, as you know, include what every batter did, play by play, the whole thing. And from that, some extremely good sports journalism can be generated. And, I don't know how many sports writers that puts out of business, but it does the job very quickly. So you can have a well-written story 20 minutes after the game's over. Okay. Let me ask you to hold that till we get to our next break, because I suspect that we are way behind on time. Automatic translation is another example of natural language processing. And you all have one in your pocket, Google Translate. It's a free app. Now, that was produced by Google, a commercial company, but they like to give things away and then sell your data. Originally, Google Translate was just a bunch of statistical rules plus a database. They went to the United Nations and the European Parliament, where the rule is any document that's passed out has to be passed out in the official language of each country. So they had this huge database of documents that have been translated by humans, human experts. And so they used that along with some statistical rules to come up with the proper translation for any word. That worked pretty well. And they did one thing that I guess makes sense to us Americans. They said there are about 2,000 languages spoken on this planet, written languages, that is. And if we have to write a translator for any one language to any other language, that would be 4 million translators. So they decided, no, anytime we get text, we're going to translate it first into English and then from English into the target language. So they only need 2,000 translators. And that system worked pretty well. But 6 years ago, they decided to switch to a different system. Machine learning strikes again. They decided to use a neural net that had been trained on millions of documents, many of them from the internet, which, as you know, is worldwide. And they are getting much better results with this neural net-based system. For instance, if you take out your phone, pull up Google Translate and type in there, hello, HASP members, it will instantly come back with, if you choose French, it'll come back with, bonjour les membres de la HASP. Story time. I did a project for Wycliffe Bible Translators some years ago, and we did it originally for the people in East Africa who all use English as their official language. And the system worked well enough. People in West Africa said, wait a minute, we would certainly like to be able to use your software, but we don't want to have to learn English to do it. We use French. Well, I took French in high school. That didn't help. So I set about translating something like 3,000 or 4,000 different error messages and prompts and so on from English into French. And I thought I would use Google Translate. But then just to be safe, I sent it off to some folks in Wycliffe who were fluent in both English and French. They laughed a lot. The machine translations are okay, but they're not human-like. Now, whether GPT-3 in a few years is going to be able to make a difference in that, nobody knows. Okay, now to my favorite subject, machine learning. And I like to think of this as the ugly duckling that became the swan. As you've probably already noticed, all the natural language processing fields use machine learning. Many of them didn't start out that way, but ML is now behind every process in natural language and almost every process in artificial intelligence. Now, some people have said, yeah, we call it machine learning, but who are they learning from? In some cases, they're learning from us. That's called supervised machine learning, where humans actually tell the machine what the right answer is and train it until it can come up with the right answer by itself. But there is also unsupervised machine learning, where people don't even know the right answer. Some definitions. Machine learning could be defined as learning a concept, like, for instance, cat, from labeled examples. And as you all know, Google did this a few years ago. They took thousands and thousands of videos that people had posted to YouTube, because Google owns YouTube, and they got people to label them. Either there was a cat in there or there was not a cat. And from that, they built a machine learning system that can identify cat videos. That is only of scientific value. I have no idea why anyone would want that. But machine learning can also simply identify patterns in data, patterns that humans have no idea are there. Another definition is machine learning is something that can learn by trial and error. A machine learning system that can start out performing poorly and by itself eventually learn to perform extremely well simply by trial and error. Now, in order for that to work, there do have to be some rewards for success, and there have to be some punishments for failure. But that's fairly easy to do. If, for instance, the computer is learning how to play Pong or chess or checkers or anything else, it's pretty clear what works and what doesn't. Now, the key method in all of machine learning is neural nets. The original idea came from a bunch of people back in the 60s who said, well, we're trying to do intelligence. That's what people use their brains for. So let's mimic the brain. It has neurons and synapses, or in computer language, we would say it has nodes and connections. Now, of course, there's a caveat. If the brain were so simple that we could understand it, we would be so simple that we couldn't. One of my favorite quotes. But they originally, there were both computer scientists and psychologists who thought that if we could build these systems built with nodes and connections, it would be such an accurate model of the human brain that we could actually study things like depression and schizophrenia in the computer instead of in humans. Boy, were they wrong. This is a very old diagram of a neural network. They called it a deep neural network, and we just laugh at that now. But this is what a neural network theoretically looks like. All the black dots are nodes, and all the lines connecting the black dots are connections. Or, the brain equivalent would be that the black dots are neurons and the lines are synapses. But the whole idea is that you put data on the input layer on the left, and it does its thing. And then something comes out on the output layer that we hope is going to be a useful answer. Now, the key algorithm that was invented many, many years ago, back in the 60s, is called the backpropagation algorithm. And it's a pretty simple algorithm. We can all understand it. At the beginning, every node in that whole system simply randomly assigns a weight to each of the connections coming into it. That's easy enough. Then we present some data on the input layer. Now, each node on the input layer then puts out a value over all its connections to the next row of nodes. And each one of those interior nodes does a computation. The incoming value on that connection times the weight on that connection. And of course, the weights were at first just randomly assigned. So, you're definitely going to get garbage. Then after each interior node has, multiplied the incoming value times the weight on that connection, they add up all those values, and that becomes the value on that node. It then sends that value over its outgoing connections to every other node that it's connected to. When that whole thing propagates forward to the output layer, we then check the output layer to see if the system got the right answer. If it's right, or if any one node on the output layer is right, we pass a reward back to each node that contributed to it. Now, if it's wrong, you pass a punishment back. And then you repeat that thousands and thousands and thousands of times. And eventually, the rewards and punishments change those weights that were originally just random into something that actually allows the network to take an input and produce the correct output. So let's just look at the diagram again. We present some data on those left-hand nodes, and they propagate their values all the way to the output layer. And then the output layer propagates back. That's why they call it the back propagation algorithm. The output layer propagates back rewards and punishments for having either helped it achieve a correct value or an incorrect value. And you do that so many times. No human could ever stand this, but the computer just does it many, 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 many times. And they're able to, quote, learn how to convert inputs into outputs correctly, usually.
What's the reward to a computer and a punishment?
Oh, okay. If I am an output node, the question was, what are rewards and punishments to a computer? A reward from the output node would be simply increasing the weight on that incoming. So if Bill's node sent me information that helped me get a right answer, I increase the weight on Bill's connection. Then I also send a message to Bill that says, hey, you were helpful. Please pass back a reward to all of your incoming connections. And that goes all the way back to the input layer. Okay? Okay. All right. Good question. Unfortunately, the field early decided that neural nets will never work. In the early 60s, they were building models that, because they thought they were mimicking the brain, they called them perceptrons, because they thought this was a model of how the brain perceives things. And there were some modest successes. But in 1968, two of the most famous AI researchers of that era, Marvin Minsky, Seymour Papert, both at MIT, wrote a paper that proved that neural nets won't work in general. They were such respected titans in the field that for 15 years, almost nobody did any research on neural nets. Hey, they proved it couldn't work. There were a few stubborn stalwarts like Jeff Hinton at Toronto, David Rumelhart, who was at Michigan for a while, Ronald Williams and some others said, we don't care, we still think this will work, and they persisted for over a decade with nothing really to show for it, except they were convinced that someday it would work out. In the mid-'80s, Jeff Hinton showed that neural nets could produce useful answers on non-trivial problems. And, you can decide what non-trivial means in that context. But things that Marvin Minsky said could not be done were done correctly by the neural nets that Geoff Hinton was producing. So the field said, oh, we goofed. The question, of course, is what really changed? How could Minsky say with such certainty, this will never work, and eventually Geoff Hinton could make it work? Well, the answer is that size matters. Back in the 70s, personal computers and VAXs, those were little mini computers, were where people were doing all their research. That every university was full of these things. And with that kind of equipment, you could produce a neural net with had maybe a few thousand nodes. And if you had one that size, even on a mini computer like a VAX, you could process maybe a couple hundred examples per hour. That may have seemed like pretty fast back then, but it was just not adequate. With machines and nets of that size, nothing really useful could be done. But out in the real world, computer games were all the rage, and they were what were driving hardware advances. As you'll remember back in the 70s and 80s, whoever could claim that their machine could process, the latest game faster with higher resolution, they sold a bunch. So fast, high resolution graphics were the key to selling hardware. Well, with this in mind, they invented something new called a graphical processor unit, or a GPU. These were not CPUs, not central processors. These were specialized processors that only did one thing. They would do the pixel by pixel computation for going from one screen to the next screen in parallel. So instead of, if you had a screen that was 400 by 500, that's what, 200,000 pixels? Instead of doing 200,000 calculations, you did one calculation 200,000 times simultaneously. Much, much, much faster. Well, these GPUs were good at doing parallel computation, and they were dirt cheap. In fact, they were so cheap that Virginia Tech shocked the world by building a supercomputer by simply taking thousands of these graphical processor units, linking them together in a communication network, and they could outperform, at that time, some of the fastest supercomputers in the world, and they built it for almost nothing. Well, GPUs were perfect for doing node by node computations in parallel. Instead of having a neural net with maybe 10,000 nodes that would very slowly grind through all those calculations to, put the answers forward and then pass the rewards back. All of a sudden, with these GPUs, you could do all those calculations so that every node was calculating at the same time. Immense improvement in throughput. The bottom line, today, you can show billions of examples to a net that has millions of nodes and get an answer in a fairly short time. Then the result has been breakthrough after breakthrough after breakthrough. So neural nets obviously have some tremendous advantages, but they can train on billions of examples, but it's costly. You have to have specialized computers full of these GPUs, and you got to pay for a lot of computer time. But once that net has been trained, it can be used very inexpensively. Neural nets that had to be done on a supercomputer that took maybe hours to produce, I can run on this little device. In fact, ever since about 4 years ago, every iPhone, and I suspect every other Android phone, has a neural processor inside. Its only job is to run the resulting networks that were produced by neural nets. So when you want to do something like voice recognition, it used to be Apple would use your phone connection to send your voice signal up to their computers. They would do the computation and send the result back. Didn't work in the deep woods. Now it's all done on the phone because you can run the neural net very inexpensively. Now, an advantage of nets is that they're trained on real world data. So they don't reflect somebody's theory, they reflect what's actually going on in the world. And that's good, but the real world contains biases and conspiracy theories. And no computer yet has been able to figure out truth from fiction. As I said before, AI is being used in the radiology field. They've recently published a paper, this one was published just last month, saying that AI can do a better job than human radiologists when it comes to identifying hip fractures. Now, that's not because somebody sat down and wrote a program to discover hip fractures. That's because a machine learning system can identify patterns in data. And after all, the trace of a fracture in the hip is simply a pattern in the data. They can do a better job than any human. So they're better than doctors at reading the scans. But again, only the human doctor can explain that. And a human doctor who looks at that scan and says, yep, there's a fracture there, can show it to the patient. They can explain, where it is. A neural net is just a matrix of billions of numbers, and its logic cannot be understood or explained by anyone, including the people that built it. It is just absolutely incomprehensible to a human. So if you want to understand why they think your hip is fractured, you need to talk to the doctor. Computer vision is something that probably you don't think about a lot. It's recognizing objects in a picture or in a single frame of a video. And the people working in this field have always been up against a real quandary. Now, physical psychologists, or whatever they're called, have measured how fast the brain can regenerate. When the brain's neurons and synapses are working, the neurons fire, and that's an electrochemical event. Then they have to rest for a very brief time, and then they are able to fire again. A human brain can recognize an image in about 100 milliseconds. And that's only enough time for about 100 cycles of the synapses firing, resting, and firing again. So 100 cycles of the human brain can recognize an image. Now that implies that the brain is using some kind of an algorithm that only has 100 steps. Computer vision programs these days have tens of thousands of steps. We don't have a clue how the brain actually does it. So this is another area where we started out saying, hey, we're going to be able to do what a human brain does. We can't figure out what the brain does, but there are some other ways that a computer can recognize a picture. Now, one early algorithm for doing computer vision was this. If you present it with an image, first of all, the computer would find the lines and the edges and the corners, because that gives it some boundaries. And then that output of where the lines and edges are would be given to another part of the program that would try to assemble these lines into features. Like, maybe there's a rectangle or maybe there's a triangle. And then another part of the program would try to assemble the features into objects or portions of objects. Maybe it's not a complete dog, but it's the back half of a dog obscured by the doghouse. And then finally, the program would try to match these observed objects with known objects in the world. If the image is one frame of a video, there was one more step. If there was a dog in the previous frame, the assumption is that there's going to be a dog in this frame, maybe in a slightly different location. And you will then pass the information on to the next frame that, hey, there's probably a dog here. That's called object tracking. Does that sound kind of familiar? Does that sound like something we just got done talking about? The picture that you input, you're inputting every pixel in the image. Well, okay, that could be the input layer of a neural net. And then some net layers early, to the left, could train themselves to find lines and edges and corners. And then the next group of nodes could learn to build features from the lines and so on. And then the output layer can just be some representation of the scene composed of known objects. This seems like an algorithm that would work perfectly on a neural net. And in fact, it does. Now, each layer might need hundreds of nodes, and the net might need hundreds of layers. There could be a total of, quite a few billion interconnections, but so what? With today's computers using GPUs, no problem. Machine learning, once again, rides to the rescue, and computer vision, including face recognition that's in the news a lot these days, all uses neural nets that have been trained in that way. Another area of AI is planning and decision making. By that, we simply mean if you give the computer some givens, like a representation of the world, that is a representation of the context in which we're going to be making decisions, and then a set of legal actions, and then a goal state. For instance, the world could be an 8x8 checkerboard. And the legal actions could be, how you jump an opponent's checker. And the goal state is to wipe out all your opponent's checkers. Well, given those three things, a planning and decision-making AI can do the following. It will first devise a sequence of moves that's going to reach the goal state. In other words, it will come up with a plan that supposedly is going to lead it to victory inexorably. And then it executes the first move. Well, then the opponent moves. And if that move by the opponent is what the system expected, then we just keep with the plan. But more likely, it will be not what they expected. So then you do it all over again. Start from the current state and come up with a plan to take you all the way to destroying your opponent, and so on. This is a fairly straightforward algorithm, in a sense. And it has been very useful in games, but fortunately, it's not all fun and games. Back in the 50s, a fellow named Art Samuels at IBM built a program called Checkers that by 59 could actually beat a human amateur. And that was considered to be stunning result. In fact, he's the guy that coined the phrase machine learning. And he called it that because he was using a database that had every possible board position in a checkers game. And each of those board positions had a score. Either if it got a high score, that meant this is on the way to victory. If it got a low score, it meant, oh boy, you're in trouble. And he would improve those scores simply by playing thousands of games against himself, or the machine against itself. And the machine learned, in that sense, how to play checkers better by refining its database of what was a good score, what was a bad score. Several decades later, some people at Carnegie Mellon and IBM built Deep Blue. Now, there had been chess programs, excuse me, there had been chess programs for quite a few years, but this was the first chess program that could beat a champion. In 1996, Deep Blue lost to Garry Kasparov, then the reigning world champion, 2-4. The very next year, beat him 3 wins, 2 losses, 1 tie in only 1 year. Now, that was not a machine learning system. That was a rule-based system. And what made it so effective was that IBM built specialized hardware that allowed it to execute these rules at blazing speed. And that was enough to beat Kasparov. But some people over in London in a company called DeepMind, which is a division of Alphabet, which is we know as Google, built something called AlphaGo. AlphaGo beat the European Go champion in 2015. Now, Go, if you're not familiar with it, it's considered to be the most complex game known to man. There are more board positions in Go than there are atoms in the universe. So any attempt to solve that problem by brute force, forget it. But AlphaGo beat the European champion in 2015, and the next year it beat the world champion, Lee Sedol. Now, it prepared for the game against the world champion simply by playing millions of games against itself. It learned from its losses and its successes, and it improved the neural net that was underlying the system. Once again, machine learning proves to be the best way. But it's not all fun and games. The thing that you are all tracking is progress or lack thereof on autonomous cars. It was 18 years ago that DARPA had the first challenge. They challenged university teams to be able to get a self-driving vehicle that could drive across the Mojave Desert 150 miles and arrive at a target at the other side. The car that got the farthest went 7 miles before it flipped over. The following year, they held the same competition, and this time, 3 different cars made it 150 miles across the desert. Now, Stanford University won with their car named Stanley, but Carnegie Mellon finished second and third. So these 2 universities made enormous progress in just 1 year in autonomous driving. In 2007, DARPA decided to issue an urban challenge. They got an abandoned Air Force base out west, and they set it up as a simulated town. The streets and alleys were already there, so they got some soldiers to come and be pedestrians or to drive other cars. And then the challenge was, get your autonomous vehicle to drive through this simulated city on a 60-mile course and get to the final destination the fastest. Carnegie finished first in that competition. Stanford was second, and my son's alma mater, Virginia Tech, finished third and was never heard from again. But this was such an exciting accomplishment that the following year, Google began testing automated vehicles on California roads. And for 2 years, nobody knew they were doing it. The only way that the cover was blown was that somebody actually pulled up next to one of their cars and noticed that the driver was playing with his phone. If he had been pretending a little bit better, who knows how long Google could have gone before they got detected. 9 years later, Google was testing automated vehicles on California highways, and this time with no driver in the driver's seat. Just a safety engineer and the passenger, who of course had a laptop, which he could press the button and immediately turn the thing off. But it took them 9 years to go from the first testing on California freeways to the point where they felt that it was safe to put the cars out there with no one in the driver's seat. It's a much, much harder problem than anybody expected. But that same year, Google, which now has named their automated driving division Waymo, Waymo launched a Robo taxi service in Phoenix. And anybody who signed up as an experiment participant could then use Waymo app instead of the Uber app to call for a ride. And if they called for a ride, a Chrysler Pacifica with all kinds of cameras and sensors on it would show up, and there would be a safety driver in the driver's seat, and there would be a safety engineer, but the car would pretty much drive itself within Phoenix. Now, if you tried to go too far outside Phoenix, they wouldn't accept the call because they had only carefully mapped the roads in Phoenix. But they launched that service, taking ordinary people for taxi rides. 4 years later, they decided it was now safe to send out the Pacificas with no driver. And they opened it up to not only test participants, but now if you were in Phoenix and you downloaded the app, anyone can ask for a ride. And the odds are that what will show up will be a Pacifica with no driver inside. Also, last year, they decided now to take a tougher problem. They're extending the Robo taxi project to San Francisco, which if you've ever driven there, you know that that is a much harder problem. But so far, they're doing very well. This is what their test cars look like. This is a Pacifica, and you'll notice that it's got all kinds of sensors. That big pod on top has LiDAR. And you'll notice on either side in the front, there are camera pods. There's camera pods in the back. Notice there's something just above the license plate. A tremendous amount of sensors are used to try to understand the road around them. Now, somebody else who's working in this area is Tesla. And although you have to, if you want to activate what they call self-driving in your Tesla, you have to pay, well, I'm not sure what you paid, Bill, but it's a lot more now.
I paid 6, it's now 12.
It's now 12, yeah, $12,000.
But you can rent it for 200 a month.
Oh, okay. But whether or not you have paid to activate your self-driving, there are 2 computers in every Tesla. One of them is running that self-driving software all the time. And the other one is keeping track of what the human driver does. And every night, every Tesla uploads to headquarters the comparison of what the software said and what the human did. Because of that, Tesla is getting millions of miles every week of real world data on what the system saw, what the computer thought should be done, and what the human actually did. Now, with that much data coming in every week, they quickly decided that there wasn't a computer in the world that could handle that. So Tesla ended up building their own custom hardware specifically to run machine learning on all that input data. Now, Waymo has also, quote, driven millions of miles, but only in simulation, which means that Waymo has only looked at situations that some human thought up to throw at it. Some people have said that this means that Tesla is really going to win the race. But Waymo is now also getting data from their taxi rides in Phoenix and San Francisco. And in my opinion, Waymo is taking a much more careful approach than I love Elon Musk. He's a great guy, but he is a little more accepting of risk than I am. He has even decided that his cars don't need LiDAR anymore. Never had LiDAR, and now they're not even using radar. It's all cameras on the new ones. Maybe he's right. I don't know. But in my opinion, trucks are probably going to be the first safe deployment of self-driving. In fact, it's already happening. There's a company called Graphical that is doing warehouse deliveries for Walmart in the South and for Loblaw grocery chains in Canada. Now, they're running autonomous trucks simply between a given store and the warehouse that serves them. That's over one well understood route that has been mapped very carefully. And even so, with these well scouted routes, they've still got an engineer as the passenger, and they've got a chase vehicle behind the truck because they think it'll work, but they're still being very cautious. Now, Graphical is using a combination of machine learning and some handwritten rules, and they seem to be doing a pretty good job. Now, Waymo is not about to be left out. They're working with United Parcel Service and also with Dodge trucks. What they're doing right now is taking parcels from individual UPS stores to the sorting center. Again, a known route, fairly short, well mapped, but they're using strictly a machine learning approach. And to my knowledge, Waymo, with all their miles in Phoenix, all their miles in San Francisco, all the miles in California, and every mile their trucks has driven, there has never been an accident that was charged to their autonomous vehicle. They have been rammed, they have been hit, but it's never been their fault. There's also a company named Aurora, which I believe is partially owned by General Motors. But they've been working with Volvo trucks on self-driving. And the reason I mention them is because you'll recall that Carnegie Mellon did pretty well in that urban challenge. They were led by Chris Urmson, who eventually left Carnegie and is now the CEO, the Chief Technical Officer of Aurora. So I think Aurora's got a good chance of coming up with some good algorithms, and they're going to put them in Volvo trucks. The bottom line is this. Driving 1,000 miles on an interstate is a whole lot easier than 10 miles in Grand Rapids. It's a narrowly confined environment. The rules are very clear, and nobody's going to ride a bicycle across your interstate lane. So, as I mentioned, all but Tesla, everybody except Tesla is using LiDAR, radar, infrared cameras. That's all pretty expensive. When Waymo first started, they were paying $75,000 per car to add all those sensors. And they quickly decided that they couldn't keep doing this. And so they set out to start manufacturing, designing, and building their own sensors. And they've now got it down to about $8,000 per car, which is good news for their experiments. But, you know, think about it. If you buy a $30,000 car and then somebody wants to add $8,000 to the price tag just so you can have autonomous driving, Bill would do it. I probably wouldn't. But, you know, on a semi truck, $200,000, another $8K, if you can possibly get permission to run 24 hours a day, no brainer. I think trucks are going to be where we first see it. Well, finally, robotics. This is the one that you're seeing. And how are we doing on? Oh, we're getting close. This is what you probably see the most about because it's so dramatic. You have seen many of the robots you see in this picture. And the two pictures down at the bottom are those things that Boston Dynamics has been building, which can do such amazing things.
Before you move on, there is a question in the chat. What is LiDAR? And I think you may have defined it, but if you could do so again.
Thank you for stopping me. LiDAR is the laser version of radar. The radar is radio ranging and detection or something like that. LiDAR is simply using lasers instead of radio waves. So it has a much tighter bandwidth. LiDAR is able to do very high resolution images of the road in front of a car. And that's what Tesla says they don't need. Okay, the methods. Surprisingly, machine learning is used in robotics, but not nearly as much. Most of robotics is concerned, at least the ones that you read about in the newspapers, is concerned with actually controlling movement in the physical world. So most robotics companies have limb and body control done through unique proprietary algorithms. So far, there has not been any one magic bullet that has been published that everybody's using, unlike so many other areas of AI. Every company has their own approach. And so far in robotics, everything is custom built hardware running custom built software. Hence, they're expensive. An interesting area of research is mind-controlled prosthetics, which is a branch of robotics. And interestingly, the military, DARPA, is funding almost all of this because so many improvised explosive devices in Afghanistan and Iraq were maiming servicemen. They were coming back to the States and the military said, we owe these guys. So DARPA has been pouring a lot of money into exploring how to not only create prosthetics, but to get beyond a prosthetic that you have to kind of manipulate through some kind of muscle. I have some prototypes that are working of mind-controlled prosthetics. It's a really exciting research area. So where do we see robots in the real world? Everywhere. Next question. This is no longer a research project. This is all industrial R&D. These are profit-making companies that are doing all the robotics research except for a few universities. Commercial and industrial robots right now are a $44 billion industry. And the projection is that industry is going to grow at 10% a year. That's a rather conservative estimate. The cost of robots keeps declining. And the cost of humans keeps going up, especially lately. So next week, we're going to talk a lot about the issues that arise when machines become attractive alternatives to human laborers. So amazingly, it's only 1/4 of, so we have lots of time for questions and comments. Question over here.
Just an overriding question. as we see what's been happening over the last number of years, and you obviously are very knowledgeable about it, where does this ultimately lead us? In your imagination, what do you see in the future?
Come back next week and we'll spend a whole hour talking about that. But the short answer, the executive summary, I guess, I think that AI research is going to continue to advance in spurts and jumps. There will be, PhD students around the world laboring hard, and 99% of them will accomplish very little, and one of them will have a brilliant idea and the whole field will advance. Things like GPT-3 will just show up and we'll be amazed at what they can do. But to steal my own thunder, the robot apocalypse ain't going to happen. I personally believe that artificial general intelligence, the ability to create something like Data on Star Trek, or the ability to create a robot that actually can act like a human in all situations, that is so far out of our reach. I don't think it's going to happen for 100 years. I have been wrong before, but my personal feeling is that we're going to see more and more advances, and we're going to talk a lot about the economic and social implications of that next week. But I do not see us getting to a world where we are simply a useless decoration on the surface of the planet. Susan.
Yes, Peg is asking, unless on next week's agenda, what will become of human employment?
All I can say there is tune in next week. That's a complicated subject. We're going to talk a lot about it.
Sounds great. And I also have just a comment. Gary, thank you for another stupendous lecture.
Ooh. Tell her I'll pay her later. Question over here. Back there.
Taking into consideration the thing of experience, the experience of a human, can that be programmed into it? You came onto it kind of when you said, can they do things that humans do, but humans are so affected by experience that can they program enough experience into robotics?
That's a really insightful question. And I guess the story I would tell is that those people who have been trying to come up with artificial intelligence programs that, quote, behave in a more human-like way have pretty much hit a brick wall. Because as you say, human beings don't start out programmed to behave in any particular way. A child is an awesome learning machine. We don't know how they do it. A child accumulates, billions and billions of sensory experiences as they are learning how to walk and talk and ride a bike and date and get a job. We have no clue how to give that kind of experience to a machine. So my short answer is that is totally unexplored territory. And in my view, that's a long, long way off if it can ever be achieved. Back here.
Sir, this has to do with the automotive industry. I had a conversation recently with someone who indicated that he believes that the purchasing and owning of cars in the future is likely to decline. And he suggested the following, that particularly in urban settings where you have self-automated cars, rather than we, as we normally do, spend about $8,000 a year to own and maintain a car, which is what he said the research indicates, we'll be moving into a time when we will no longer buy cars, but we will share in automated cars that run 24/7. Can you comment about that?
Yeah, great question. I know somebody else who feels that way. He's the CEO of Ford, who said several years ago, the future is not going to be two Fords in every garage. The future is going to be transportation as a service. And that phrase has become so common that it's now often just abbreviated as TaaS. But transportation as a service is what most observers feel is in the future. Not next year, maybe not even in the 2030s. But as self-driving cars become so reliable and so safe that we can use them in general, and we're still a ways from that. But when that day comes, especially if the Waymo approach with all those sensors prevails, and I think they will, a self-driving car is going to be a fairly expensive item, but it's able to run 24 hours a day, 7 days a week. It doesn't really need to go into parking garages. It can find little places to hide when nobody wants it. Transportation as a service will supplant car ownership, certainly for the majority of urban residents. What will happen, out in Borculo is not so clear. But for, way over half of the US population resides in cities. And even in a city the size of Holland, if people can get away with not buying a car, insuring it, maintaining it, by simply, using an app to call for transportation whenever they need it, that's a no-brainer. But it's, the machines are probably at least 10 years away from being able to do that, but it's coming.
I think we had a monthly HAS presentation by somebody talking about the self-driving cars about 2 years ago. Well, I don't know, COVID time, but my question is Siri listening to us now, and is she going to have all kinds of AI stuff come up on my phone and et cetera later?
Well, I know Apple's official answer to that, which is that Siri does not listen until you do one of the gestures that calls her up. Either on the phone, it's like, holding the button for a couple seconds. And Alexa supposedly doesn't listen in until you say, hey, Alexa, or whatever. The problem is these devices all have to be listening in order to listen for their call phrase. And furthermore, I mean, when the brouhaha hit about Alexa or about, Google capturing all these normal conversations, everybody was concerned that they were trying to, spy on your fight with your husband, when in fact, these were a bunch of very earnest researchers trying to improve their speech understanding algorithms. And as you've seen from this lecture, everybody knows now the way to do that is to get millions and millions of examples and feed them into a neural net. They were just trying to get more examples. Since all the firestorm over that, I think Google has tried to placate us by reducing what Alexa and others have to listen to. But Alexa still has to listen for her call. If she doesn't transmit anything except what you ask her, I think that's all we can ask. Good question. Any questions in the chat, Susan?
No, that is it. If you are at home and you need to ask a question, you can unmute yourself if you would like.
We have a question in the classroom here.
Yeah, I'm not sure exactly what this is called, but there's something I've been reading about. It's a 3-word designation for every 10-foot space on the planet or in the country. This is something that would be, there would be like 3 common words that would tell you, would direct you or direct a car, I assume, to a particular 10-foot space. Are you familiar with that?
No, I'm not.
Oh,
Sorry. But you can Google it.
I am, and I'm Googling it right now to see if I know what you're talking about, but it's very interesting. I'll see if I can find the name and put it in the chat. And
So if you're interested in that question, see Susan after class.
You mentioned the good record so far. Is it true that basically we will end the era of millions of people like my grandma dying in automobile accidents when autonomous vehicles take over and get rid of the texting teenagers and everybody else who's been causing all these problems?
Again, we'll have to steal some thunder from next week because that's one of the topics we're going to talk about. But yeah, a lot of people, specifically Chris Urmson and his colleague, whose name escapes me right now, both of them lost friends in their teenage years to auto accidents, and it's why they're doing the research they're doing now. I agree with them that someday it will be illegal for a human to operate a vehicle on a public street. But that day is a long ways off, unfortunately. The fellow who made that video called "Humans Need Not Apply" had a brief comment about self-driving cars, and this was done maybe 7 or 8 years ago when everybody thought this problem would be solved by now. He said, yeah, self-driving cars aren't perfect, but they don't have to be perfect. They just have to be better than us. Well, for reasons that we'll discuss next week, no, it's not enough just to be better than us. Any other questions before we all, Bill?
Susan, did you find the 3-word thing?
It's an app called What 3 Words, and
Yes.
it's what and the numeral 3 and words. And I'm sorry, I didn't mean to jump in,
No.
but it is a very interesting, it basically breaks the entire earth down into 10-foot squares. And you can all look at it. It's a topic for a different day, but
That's
do we
your
have any-
homework.
Yeah. Do we have any more questions in the classroom?
Then I think we can all go to lunch early.
Gary, thank you.
That sounds great. Thank you so much, Gary. We appreciate your contribution to HASP. And for those of you at home, have a very wonderful day.